All right, yesterday we looked at the graphs of these parabolas right here, which aren't necessarily parabolas, but they could be any kind of polynomial. And we talked about the low points, which occurred in the valleys, and we talked about the high points that occurred on the hills. And we called the y values at the low points, we called them local minimums or relative minimums, and they occurred at the x values. Similarly, the y values that occurred on the hill were the local maximums or the relative maximums, and they occurred at the x value. And we used the calculator yesterday to find the values of the local max and local mins and their locations, because sometimes it's very hard to find them unless you know calculus. So that's where all this is going later with calculus. So if we quiz tomorrow, I'll have you find the local max and local mins. You will have a calculator, or you're going to be welcome to come use one of mine. So remember how we did that. We graphed it, and then we went to the second trace, which is the calculate menu. Max, min are the options. You do left bound, right bound, and then you can use the right bound for your guess. So as you're practicing on the homework, if you need to borrow a calculator, come let me know, or come in the morning and you can borrow one. Okay, so what we're going to do now is look at another application of these functions. These functions that we look at here, they're curvy. So the y values are changing as we go from left to right. And sometimes we might want to know how fast are they changing. Well, calculus answers the question, how fast are they changing at any given moment? Without calculus, all we can do is answer the question, how fast are they changing on an interval? Okay, and whenever we talk about how fast something is changing on an interval, we're talking about the average rate of change, okay? The average rate of change between 2 points on the graph. So if we think about the application of this from physics, you figure out average rate of change of position all the time. If you talk about how the position is changing, you're talking about what quantity? Man, look at his position change. He is fast, right? You're talking about his what? Speed, right? Or velocity. So the average rate of change of position is known as the average speed or the average velocity. So let's say that you drove a total of 130 miles in one direction, and it took you 2 hours to travel 130 miles. You could figure out your average speed for the whole trip, right? The average speed is your total distance traveled, sometimes called your displacement if it's in one direction, displacement, over the elapsed time. So if you travel 130 miles total, that's your aggregate total distance over the total time, 2 hours. Notice your units, first of all, when you do the division, is miles divided by hours or miles per hour. You average 65 miles per hour. Now, does that mean that you're traveling 65 miles per hour necessarily the entire time? No, probably not, right? Unless you're on cruise control and you're 65 the whole time. Normally, you start from 0, you accelerate, your stop signs, right? You sometimes exceed 65, then the cop pulls you over for speeding, so there's that time where you're not doing anything, right? And then you pull out and you drive the speed limit after that, right? Drive the speed limit the whole time, right? What is the speed limit now? Back in my day, it was 55, constantly on the highway. And that was hard to do. But now, 70 is the norm, right? And then what's that? 80 in some spots. 80 in some spots, yeah. And even if you get out like past Kerrville on I-10, it's even 85 in a couple of spots. And you can make up some time. But anyway, to find the average rate of change of position, it's the average velocity. Now notice, just because we know this, it was the average over the 2 hour period, it doesn't give us any information about what was happening at any specific time during the 2 hours. We just have 2 points. We have the starting point and the ending point. Here's how the calculation would look if we actually had a function d of t that represented the distance that we traveled over the 2 hour period. It would look like this. It would be your position at 2, so it would be the function d of t evaluated at 2. That would be your final position, minus d of 0, that would be your initial position, all over 2 minus 0. This is what we call the difference quotient. And the difference quotient is very, very important. In Algebra 1, when you found the slope of a line, you used delta y over delta x, right? It was y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's all this is. It's the quotient of two things being subtracted, the change in the y values over the change in the corresponding x values. Whenever you're finding average rate of change, whether it's for a test or a quiz or whatever, you must show me the difference quotient. You must show me the setup that you're subtracting two y values minus the change in two corresponding x values. Okay, let's look then at the box here. It says the average rate of change on a closed interval of some function f of x between two x values, call them a and b. So when we say on a closed interval, we could write it like this as well. How do I know that's a closed interval? Brackets, right? A inclusive, everything between a and b on the open interval, and then including b at the end. If I want to find the average rate of change, you know, to throw a bit of Ireland in there, it would be just like in Algebra 1, delta y over delta x. But now, because our function is f, and our values are a and b, it's f of b minus f of a over b minus a. And again, what do we call this piece right here? The difference quotient. All right. Now let's look to see graphically what the average rate of change would manifest as on a graph that's curvy. On a line in Algebra 1, the average rate of change is just the slope of the line. And you remember from a line, the slope is the same everywhere along the line, right? So what's interesting about a line is the slope at any given point is the same as the slope between any 2 points on the line. It's constant. But when we have curves, that's not true. The slopes vary on a curve. So if I want to figure out, for instance, how fast this graph is changing from x equals a to x equals b, that is from this point here, af of a, to this point here, bf of b. I know that it looks like it's going up on the interval, right? But I want to know essentially how fast is it going up on average. If I just did f of b minus f of a over b minus a, what I'm doing is I'm finding the slope of a line. This gives you the slope of a line. Every time it gives you the slope of the line. I'm going to leave a little blank in front of the line. The line that we're finding the slope of would be this line right here. Okay? And it kind of bends. Let me try that again. It shouldn't really bend down there. So this is a line that intersects the curve at 2 points. And when I find the slope of that line, I'm finding the average rate of change of the function between those 2 points. Does anyone know what the name of this line is that intersects the curve at 2 points? I think you encountered it in geometry when y'all were talking about circles. The tangent line is the one that touches the curve at a single point. A chord is a good name, right? A chord is a segment that intersects the circle twice. If you extend the chord out to infinity, you get what's called a secant line. Yeah, it's called a secant line. So when you're finding the average rate of change of a function that curves, you're still finding the slope of a line using the difference quotient between those 2 points, but it ends up being the slope of the secant line. So those are now mathematical synonyms. Slope of the secant line is the same as the average rate of change. The average rate of change is the same as the slope of the what line? Secant line. They're mathematical synonyms. They're interchangeable. Okay, so notice there's 2 ways then to get from af of a to bf of b. You could follow the path of the curve, which kind of goes up pretty fast to start with. It's pretty steep. And then it levels out and approaches b. Or you can get there at a constant rate, right? Go up, over, up, over, up, over, up, over, by whatever the slope of the line is. So it'd be the difference between you and your friend starting at your house and you're going to San Antonio to whatever. Let's just say you're going to the Forum and you're meeting at Bath and Body Works. I don't know, because you need some more soap. They have vampire blood, by the way, over there. If you want to go, it's like intense plum, but it says vampire blood. It's Halloween. They were sold out on Saturday. But anyway, let's say you're going to go meet your friend at the Bath and Body Works store to get some vampire blood soap. You go ahead and obey the speed limit, right? The stop signs, the stop lights, so your speed is varying. But your friend, you kind of let him get a running start or a driving start, and they're going 65 miles per hour the whole time on cruise control, right? They have some secret road that goes straight to there, so they don't have to break any laws to do that. You and your friend can arrive at the destination at the same time, right? She's going 65 the whole time. You're obeying the stop signs, and you're going 70 sometimes. It is possible. So your friend on cruise control would be getting there according to the rate of the line right here. They would be going at a constant rate from A to B. You, on the other hand, your speed might vary. In actuality, it may be something like that. But it's possible that y'all can leave at the same time and get there at the same time and have speeds that vary. So that's the difference between the average rate of change and the instantaneous rate of change. The instantaneous rate of change would be what your speedometer on your car is reading at any given moment. And to figure that out, you need calculus. But to figure out the average rate of change on an interval, you don't need calculus, you just need algebra. It's the slope of the secant line. Yes, sir? Huh? Oh, you can look in a car, just look at the odometer, right? Seriously, you can measure distance is something that we can measure, right? We can physically measure distance. We have odometers that do that now. We have wheels that track distance. You can just walk with them. We also have tape measures. Some of them are pretty darn long. Distance is an easily measurable quantity, yes? And time is an easy thing now to keep track of. So if we can keep track of total distance, then we can keep track of total time, which is relatively easy. We can figure out the average rate of change or the average velocity. All right, here we go. We're going to try it on example 4. We're going to look at the graphs of x minus 4 squared, and we're going to find the average velocity or the average rate of change of the graph on the following closed intervals. Now we're going to do it with the graph first, because we're going to review transformations. What's the parent function for this function? It's parabola x squared. And what does the minus 4 on the inside do? Moves it right 4. So I'm going to come down here and kind of draw a large graph, because we're going to refer to it multiple times. Moves it right 4, y'all said. So I'm going to call that 4, and here it goes. Boing. There you go. And now what we're trying to do here on part A is we're trying to find the slope of the secant line, or the average rate of change. Notice the notation there. How would you read that? Yeah, it's on the closed interval from 2 to 4. We know it's an x interval. X is, included in the interval from 2 to 4. The x values are elements of the interval from 2 to 4. So that's just another way to clearly define that it's an x interval that we're looking at and not a y interval. All right, so let's come over here and plot those points. 2 is going to be right about here. Actually, maybe I should, in hindsight, move my graph over a little bit just to give ourselves more room. You could do that easily with Notability, right? Just lasso and move. Okay, cool. Lasso with scissors. I love it. All right. So 2 now would be right about here. Now it looks a little bit better. So there's 2. Here's 4. I want to figure out the average rate of change from 2 to 4. Just looking at it, is it going to be a positive or a negative number? Negative, because what are the y values doing on that interval? They're going down. Now, they're going down at a variable rate. Would you agree? At 2, they're going down a little bit faster than they are as you get closer to 4. So I want to figure out the average rate of change, which would be the slope of the secant line. And again, if you mess it up, just kind of move it. There we go. If I can find the slope of that line, that's the secant line again, I could figure out the average rate of change of that particular function from 2 to 4. So let's go for it. What are we going to show? What must we show when we're finding the average rate of change? The difference quotient. Okay, so here's what I'm going to, my function's name is f. So I'm going to label it as average, and it's going to be f of 4. That's like my final position, or the final y value, minus f of 2, the initial value, all over 4 minus 2. Is that a difference quotient? Yes. Yeah. Now here's kind of just a little note. Remember in Algebra 1, you could put the ordered pairs in any order you want, as long as you did the corresponding change in the denominator. So you could do f of 2 minus f of 4 over 2 minus 4, and you'll get the exact same number. You'll get the exact same number. However, I would discourage you, bless you, from doing that, because when we start getting into the applications, when you do f of 4 minus f of 2, that is the position at the right endpoint minus the position at the left endpoint, the numerator now becomes meaningful. It's the displacement. It's your final position minus your initial position. But if you do f of 2 minus f of 4, that's not your displacement. So get in the habit of doing final minus initial. Okay, so now that we've shown, what's that? Well, if it's an open interval, you technically can't include the endpoints, right? And it's hard to figure out what the average rate of change is on an open interval, because you would have to then look at the very first x value after 2, right? And what is the very first x value after 2? I don't know either. 2.000, we can keep going, 000. I want to take a chance at a 0.000, so we can all say 0 and keep going. There is no number. So the fact that it's a closed interval is nice, because it's like, now we have a place to start, okay? All right, so now that you have the setup shown, and you would get a point for this, by the way, now it's time just to evaluate it. So working straight down, what is f of 4 by direct substitution? 4 minus 4 is 0. 0 squared is 0. Minus, plug in your 2, f of 2. That's 2 minus 4 is negative 2. Negative 2 squared is? Huh? By direct substitution. F of 4. F of 4. Oh, yeah, we have to plug it back in. Absolutely. These are y values, right? Here's my y value machine, right? F is just another name for y. If I want to know what the function value is at 4, that's what function notation works. F of x equals x minus 4. So when x is 4, f of 4 is 4 minus 4, which is 0 squared, which is 0. And we knew that, right? That was our x-intercept. That was where the vertex was. So what's f of 2 again? Plug it in here. 2 minus 4 is negative 2. Negative 2 squared is 4. There's your numerator. And, of course, what's the denominator? 4 minus 2 is 2, and we end up with negative 2 as an answer. So, yes, once you show the setup in function notation, then it's time to evaluate it, depending on what your function is. So what does that mean? That means as the graph goes from left to right, from x equals 2 to 4, it goes down, on average, 2 units for every 1 unit it goes to the right. Now, if we were measuring something's position, we would say the velocity of that object is negative 2 meters per second or something like that. Or we would say that the position is decreasing by 2 meters per second, which means it's probably moving down or to the left, depending on which type of motion you're talking about. Average rate of change. It's the same as average velocity when you're talking about the change of position. Okay, let's look at B. Is this another closed interval? Yes, but notice it's given indifferently. This is interval notation. This is inequality notation, but it's really the same thing, right? This is from 5 to 8. So we'll put the average rate of change then is, let's do the setup first, and then we'll go look at the graph. What's the setup? If I need to show the what quotient? Get in the habit of not f of 5 first, but f of 8. Do the final one first. Minus f of 5 all over 8 minus 5. That right there is the difference quotient, and that's going to earn you a check. Now, to evaluate the numerator, I've got to figure out what is f of 8 and what is f of 5. I'll plug into my function, right? 8 minus 4 squared is 16. 5 minus 4 squared is 1. All over 8 minus 5, which is 3. So our final answer is 16 thirds, or if you simplify that, 15 thirds. Thank you. Careless mistake. Which is what if it simplifies? That's a lot better. 5. Yeah. So without looking at the graph, because we haven't looked at it yet, knowing that we got an average rate of change of 5, that means that on average the graph, as we went from 5 to 8, was going up 5 units. For every 1, it was going to the right. So if this was describing the motion of something, the object would be going in the positive direction by 5 meters per second. Okay, in this case, it's going up on average. Does that mean it was going 5, a slope of 5 the whole time? Up 5 over 1, up 5 over 1? No. Yeah, that's just the average, like if it was on cruise control. Let's see what that looks like now from 5 to 8. Coming back here to the graph, 5 would be, let's use green. 5 would be right about here, and 8, if I extend it out, would be, let's say, right there. Now, just because I know that the average rate of change was 5 the whole time, that was the slope of that secant line, did it have to be going in the positive direction the whole time necessarily? No. Just the same reason, like if you are traveling from here to San Antonio and your average speed is 60 miles per hour, that doesn't necessarily mean that you're traveling south on 35 the whole time, right? You could have started heading south and realized right away that you forgot something at home. You could have turned around, gone back towards, Austin, towards the north, and then turned around and gone back and still average that. You would have to define between 2 points. Yeah, between 2 points. Now, here's my question, which kind of gets into the calculus part again. If the average rate of change of the graph is 5, let's just say that to get from 5 to 8, on average, it goes up 5 over 1, up 5 over 1. It wasn't necessarily going up 5 over 1 the whole time because, of course, it's not the line. Did it have to be going up 5 and over 1 at least one time during that interval? If you think about it in terms of your trip to San Antonio, if your average speed to San Antonio was 60 miles per hour, did you have to necessarily be going 60 miles per hour the whole time? No, but was there at least one time in your trip where you had to be going 60? I think we can all kind of say intuitively, yeah. Yeah, there's no way to get an average of 60 unless you were going 60 at least once. Okay, this is getting into the calculus. Here's what that would look like. There has to be at least one place then where the instantaneous rate of change would equal the average rate of change. So if I copy that line, which makes it parallel, if I can find a place where it just touches the graph at one point, watch this. Right there. You see that? Right about there, this line, this secant line that I moved over that is now parallel, it touches the graph at this single point. Guess what that line's called? That's called the tangent line. A line that touches the graph at one point is called the tangent line. And if I could figure out what that value is, I would then know essentially at what moment exactly I was traveling at that speed if this modeled my rate of change of position. Now, can we figure out what that is for this problem? Is there a way to figure out, okay, it averaged up 5 over 1 on this interval, but I know it had to be going up 5 over 1 at least at one x value on the interval. Is there a way to figure out that x value now? What do I know the slope of this line to be? 5. I would have to be able to have an equation that gave me the slope at a given point, the instantaneous rate of change instead of the average. If I knew that, then I could set it equal to 5 and solve. We don't know such an equation. Galileo was searching for such an equation his whole life, and he never did find one. But you know what? There is a way to find it. We would need calculus to find it. And that's what calculus is all about. Finding these places where the instantaneous rate of change exists by formula. Huh? Oh, yeah, it's been found big time. Yeah. Newton and Leibniz invented calculus after Galileo. Galileo was interested in finding the instantaneous rate of change. When he had the little experiment where he was rolling those balls down the inclined plane, he was trying to figure out their instantaneous velocity. But he didn't have any formulas to work with, so he did it empirically. He would measure where is the ball at to start with, where is the ball at in the closest instance after that he could possibly measure. And he was finding the average rates of change of the position of these balls over a very, very small time interval. The instantaneous would be at one point, good, at one instant. And you need calculus for that. That's what calculus gets into. The average rate of change is between 2 points. Yeah. Now on a line, remember, the instantaneous rate of change is the same as the average rate of change because it's the same slope everywhere. But most things in this world change. They're not constant. So there is a way to figure out that instantaneous rate of change. So that might be a little motivation for you to sign up for calculus next year. It's a lot of fun. So right now we're going to stick to average rates of change, and we know that the average was 5. But looking forward, there is a place where it had to be going 5 at least once. All right, do this one on your own. I'm going to give you about a minute. Find the average rate of change between 1 and 9. Show your difference quotient. While you're doing that, I'm going to sketch it on the graph so we can see what your answer means. You're going to answer? 0 over 10? What is 0 divided by any non-zero number? 0. Yeah, 0 over 0 doesn't work, but 0 over any non-zero number is 0. So y'all should get 0. Did y'all show this? F of 9 minus f of negative 1 over 9 minus negative 1? Now, if it is 9 minus negative 1 and you want, you can just call that 9 plus 1, and that would still be considered a difference quotient. Okay? Y'all ended up with what in the top? 10? Oh, 0. Y'all ended up with a 10 in the bottom. Yeah, and 0 divided by 10 is 0. So 0 is a very, very nice number because if that's the average rate of change, that means that you average 0 miles per hour over your whole trip. How could you average 0 miles per hour over your whole trip? Yeah, in the first case, you don't go anywhere, right? If I stand still on this little square right here for 2 hours, right? Maybe challenging David Blaine to that stunt. I have gone nowhere over 2 hours, so my average rate of change is 0. But is it possible for me to actually go somewhere and still have an average rate of change of 0 if I'm not driving? What if I start here and I go walking around for about 2 hours, and at the end of 2 hours, I end up right back where I started? My final position and my initial position are the same. What's my displacement? 0. What's my elapsed time? 2 hours. What's 0 divided by 2? 0. So you can have an average rate of change of 0 and still have gone somewhere in between. But if this also represents the slope of the secant line, what kind of line has the slope of 0? Horizontal line. A horizontal line has a slope of 0. So this is what we just found right here. Here's negative 1. Here's 9. Notice the vertex is 4 away. Parabolas are symmetrical through the vertex. So 9 is 5 units away to the right, and negative 1 is 5 units away to the left. So it does have symmetry through the origin. We do have the slope of this horizontal line.
If we have a parabola and we know that it's the equal amount,
then you know it's going to be 0, but guess what you still have to show me? You still have to show me the setup, yeah. Yeah, so very important. These slopes of zeros are very important. Now, let's go back to what I just talked about. If the average rate of change on the entire trip was 0, did there have to be a time between negative 1 and 9 where the instantaneous rate of change was 0? Where the slope of the tangent line was 0? Heck yeah, let's see what that would look like. Yes, very good. That's at 4. And what's the significance of 4? It's the vertex, or what we called it yesterday. It's the location of the local or relative min. Yeah. And when you get into calculus, finding the location of these local mins and local maxes is very important. We did it on the calculator yesterday, but if I could figure out where the instantaneous rate of change is 0 for a function that's not a parabola, something that looks like that, what if we're measuring cost against units produced? Do you think it might be useful to know where the instantaneous rate of change is 0 right here? Or where the instantaneous rate of change is 0 there? Sure, we need calculus for that, but this is going to be where my cost is at a minimum, and this is going to be where my cost is at a maximum. And if you're running a business, you might not want to have your costs at a maximum, right? So this would kind of give you an idea of what level you need to be operating at in order to minimize your costs. Or if this were profit, you might want to be maximizing your profit. So that's where all this is going with calculus. But right now we're just finding average rates of change, which is the slope of the what line? Average rate of change is secant line. You don't need calculus for average rate of change. Here's how you can remember. Algebra is all you need for average rate of change. Algebra, average rate of change. They both start with that annoying sound. You got a question? Good question. Just like an x cube? There would be no local max or local mins. Right? There is no local max. What is the instantaneous rate of change right here at the origin? 0. But it's only at that instant. That's not a place where it turns around. So this would be a prospective place where it could have turned around. That graph, if it wanted to, could have come up here and bounced off the x-axis and gone down and been a local min. But instead it went psych, and it juked and it scored a touchdown. Okay? Not every function has local maximums. All right, any questions on average rate of change with graphs? All right, let's look at an application. This would be kind of the Newtonian perspective. Newton was the guy who was motivated by motion to come up with the calculus. When a Precal textbook is dropped from the top of a tall tower, it's been known to happen. Back in the days where we had Precal textbooks, people took out their anger and frustration on the poor textbook themselves. And I don't even know where people would have access to a tall tower in the back of the school. But anyway, it happened. The distance that the book has fallen, the distance that it has fallen, not the height above ground, but the distance it has fallen from the top, t seconds is given by the function d of t equals 16t squared. Find the book's average speed over the following intervals. Okay, so here's an application. We want to look on the interval from t equals 1 to 5 seconds. So, what do we call the average rate of change of distance? The average speed, or in this case, we'll call this average speed. So we can actually label it now. The average speed is going to be, our function is d, so d of 5 minus d of 1 all over 5 minus 1. Now that's all we're doing. We're finding the slope of the secant line, but it's giving us the average rate of change of the book's distance. This is displacement over time. This is physics. This is displacement, the net change in position, your final position minus the initial, over the change in the time, the elapsed time. All right, so let's go ahead and compute it. What is d of 5? Well, it's 16 times 5 squared minus d of 1, which is 16. All over 5 minus 1 is 4. Now let's look at the units, because the units are very important when you have an application. What are the units of the numerator? What are the units of distance? Are you okay with this? I don't have a calculator, so I just did 5 squared times 16. There's my d of 5. Minus, I do know 1 squared is 1 times 16 is 16. I'll get back to simplifying that later. What are the units of distance? What are the units of the numerator? I don't even think I give it, huh? Let's give let's make the tower, let's measure in feet, okay? I should have put units in there. I need to adjust the question. So we're going to measure it in feet. So distance would be feet, and the time is in seconds. And so the units will work out. It's kind of like stoichiometry, dimensional analysis. If you put the units in your calculations, what are your final units going to tell you? That you're finding something that's in feet per second, which is a measure of speed. Now, without a calculator, how would we evaluate that? You could do that first. I would notice that I have 2 terms in the top, and the 16 is a common factor. So before I just carelessly divide out the 4 from one of the 16s, I would factor it out first. I get 5 squared. I can call that 25. I think I know that. And what do I get when I factor a 16 out of itself? A 1. Good. All over 4. Now I have 16 times something over 4. Now I can divide out the 16 fourths, right? What is 16 fourths? 4. And what's 25 minus 1? 24. That makes it a little bit easier. 4 times 24 is 96. I factored the 16 out. You don't do it with numbers that often, right? You're used to doing it with variables. But look, redistribute. 16 times 25 is 16 times 25. Minus 16 times 1 is 16. It works. I factored the 16 out so that I could divide it out with the 4. You notice that we could divide out the 4, but you know what? If people do it up here, guess what I see them do? They do it like this, and they don't ever take care of the other 16. So that would be RONG, wrong. So whenever you're dividing something out, I do want to see the factored out step. So this is a way to kind of keep the number small when you don't have a calculator. This is a little bit of number sense, a little bit of agility. It's 96 feet per second. That was the book's average speed during that 5-second interval. All right, now what is it going to be between A and A plus H? Well, let's go ahead and write it. The average velocity is going to equal, setting it up, it's going to be the distance at A plus H minus the distance at A. We don't know what A is and we don't know what H is, but apparently A is going to be some arbitrary time and H is going to be some distance or length of time past A. So like if A was 1 and H was 1, this would be from 1 to 2, 1 second later. All over the corresponding change in the x value. D of A plus H minus D of A over A plus H minus A. Now if I simplify the denominator before I plug in, what happens in the denominator? What's A plus H minus A? H. Have y'all seen this expression before? Yeah. Where? It's my favorite problem. It's the one from the test, the last two tests, right? The last question on the last two tests. Why have I been making y'all do that on every test? Because I'm cruel or cool? Either one. I didn't hear, but I'll accept either one. Yeah. It's because it's important. This is an application of the difference quotient, which gives us the average speed. Let's go ahead and plug it in. Remember, our function is 16t squared. So this should be a routine calculation now. d of a plus h is going to be 16 times a plus h squared, minus d of a is going to be 16 times a squared, all over h. We're plugging in an a plus h, and then we're plugging in an a. 16 blob squared minus 16 blob squared. All right, now once we set it up, you know what to do, right? We're going to expand it. I'm going to square, multiply, double square, and distribute the 16 at the same time. You ready for that? We can do that now. So square the first, you get a squared. Distribute the 16, you get 16a squared. Multiply and double, and you get 2ah. Distributing the 16, you get 32ah. And then you square the last, you get h squared. Distributing the 16, you get 16h squared. And then minus 16a squared at the back end there. So we expand it out. And remember, if we expanded it out correctly, or in this case, set it up and expanded it out correctly, good things should happen in the numerator, right? 16a squared, see, it wouldn't want to be, everything that's left has a what in it? Has an h in it, which we can now factor out first. You must show the factoring out step. So I'm left with 32a plus 16h all over h, and then everyone's favorite step, right? What? You could, right, yeah. My goal is to get rid of the h in the denominator. There is a common factor of 16 that you could factor out. Now that those are gone, I am left with 32a plus 16h. And notice that gives me the average velocity between any 2 points from x equals a to x equals a plus h. So here's what's the smart thing to do. If you wanted to figure out what the average rate of change was multiple times, like from 1 to 5, and then from 2 to 6, or from 2 to 3, you wouldn't want to have to set this difference quotient up each and every time, would you? What we did then is we were smart about it. We let 1 equal a, essentially, and the distance between 1 and 5, that's 4 seconds. That's a span of 4 seconds. We're calling that h. And by leaving it as a and a plus h, we have now come up with a formula that allows us to figure out the average velocity between a point A and another point that's h seconds away. So let's verify this one over here. Using our formula now from part A, our value of A was 1. We started at 1, and 5 seconds was 4 seconds later, right? So in example A was 1 and h was 4, because we went from 1 to 1 plus 4. Let's see what the average velocity is now by our formula. If I just plug in these values here into our formula, I get 32 times 1 plus 16 times 4, and that gives us 32 plus what? 64, which is 96. And we get the same answer. That's pretty cool. And we don't have to set up the difference quotient again. Let's figure out the average rate of change, or the average speed now, from a equals 2 to a equals 3. Are you curious? Oh, yeah, h equals, well, from a equals 2 to h equals 3 would mean h equals 1. If I want to look on the closed interval from 2 to 3, I want to start at 2, and I want to let 1 second elapse, right? H is the number of seconds you let elapse. If I plug it into my formula now, let's highlight it. Let's see what I get. The average speed then on that 1 second interval is going to be 32 times 2, which is 64, plus 16 times 1 is 16. We end up with 80. Yeah.
So are the points, or not points, but are 2 and 3, is that time?
That's time, yeah. From the second to the third second. We're going to let A equal our starting time, and then H is the amount of time we let elapse. That's what H is. So if I go from 2 to 3, we're starting at 2, and H is 1 second elapsed. Now notice what I'm trying to do here. Let's see if we could figure out what the average speed is This will be our last calculation. From 2 to 2.0 or to 2.1. That's only a tenth of a second. Is it possible to measure something in a tenth of a second empirically? Maybe now we have the instrumentation to like let a tenth of a second go by and measure where something's at. But in Galileo's day, that was really hard, really hard. We could do it by formula now because for us, A is 2 and H is what? 0.1. I can plug it now into my little handy-dandy formula, which I have written in my handy-dandy notebook. So the average speed on that tenth of a second interval is going to be 2 times 32. That's our A value, which is 64. Plus, what's 16 times 0.1? Right, which is 1.6. Right? And that's going to be 65.6. Okay? What if I let even less time go by, from 2 to 2.01? That's 100th of a second elapsing, isn't it? That's like very little time. A would be 2 and H would be 0.1. My average speed on the interval then is going to be, if I plug it in here, 2 times 32 is 64 plus, what is 100th of 16? 0.16. I get 64.16. Now, if I was interested in what the instantaneous speed was at 2, what's happening to this last piece as H gets smaller and smaller, going to 0? As H goes to 0, 16H goes to 0, right? And guess what the instantaneous speed would be at 2? 64. That's sneaking up on the tangent line. That's the seed of calculus. Y'all have a great day. You can't let H be 0 because as soon as H is 0, how many points do you have? 1. And you need how many points to find the slope of a line? No. And it's a subtle difference. What you're saying is let H equal 0. And if H is 0 in this equation, we do end up with 32A. That becomes a derivative formula. But we can't physically let H be 0 because then we have 1 point and there's no 2 points anymore. But you have it in your head now. What we're going to do in calculus is we're going to take the limit as H approaches 0. And there's a subtle difference. If you let H approach 0, you're never claiming it has to equal 0. And that way you're still using 2 points. And what happens is the secant line slope approaches the tangent line slope. And once we divide out the H over H up above, we are going to be allowed to use direct substitution to evaluate the limit. So you're thinking ahead. You want to invent calculus right now in your head. But you can't let H equal 0. You can't let H equal 0.